My presentation is called Analytical Computation of the Radiation Emission for Circular Geodesic Orbits Around Black Holes. This was a work that I done in collaboration with Professor Rafael Bernat and Professor Luis Crispin. And here is a brief summary of the presentation. I will start with an introduction and motivation of the subject. Then I will make a quick review of Hahn functions and the theory of differential equations based on their singularities. Afterwards, in section 3, I will apply all this mathematical machinery that we developed in section 2 to explore the radiation emission, the scalar radiation uh, in Schwarzschild spacetime. And then I will end up in section 4 with some conclusions. So I think we may start with the introduction. And well, this problem of geodesic synchrotron radiation is basically you consider a particle that is orbiting a black hole in a circular geodesic, and you calculate the radiation emitted to infinity. And this is a problem that was already explored in the literature. Maybe the first paper, at least that I know of, that make this calculation is this paper here, where they basically use the WKB approximation to find the analytic expression for the green function of the radiation field. And some decades later, Professor Crispino, Atsushi Higuchi, and Matsas published this paper uh, using quantum field theory in curved space-time approach to make the same calculation. And they solved the radial equation for the radial modes using numerical techniques. And last year, we were able to publish this paper in Physics Letters B, where we revisit this problem, but now applying some analytical techniques, namely the theory of fine functions. And that's what I'm going to talk about right now. And so in this section, I intend to address three questions. The first one is, what are Hahn functions? Why it is important? And what do we need to know about it? Well, at least for the sake of this presentation. So this is a picture of the paper published by Hahn, where he, for the first time, uh, written down the Hahn equation, that is this equation over here. We use a different notation that he used in this paper. And here I have the first definition of the presentation. What is a Hahn differential equation? It's the general second-order linear Fuchsian equation with four singularities. Maybe the name Fuchsian equation deserves some explanation. Roughly speaking, a Fuchsian equation is an equation which all their singularities are regular singularities. So the Hahn differential equation is a differential equation with four regular singularities. And normally we display the Hahn differential equation in its canonical form. And it's given here in equation 1, where these functions P and Q are these functions given here in equation 2. In these functions P and Q, we have some parameters. Gamma, delta, epsilon, alpha, and beta are called polynomial parameters. Q is called an accessory parameter. A is called a singularity parameter. The polynomial parameters must satisfy this relation over here. And I told you that this is the canonical form of the Hahn equation, but I didn't told you what a canonical form is. So a canonical form of a differential equation is basically when these functions P and Q only have simple poles. So you cannot have nothing like a z squared or z minus 1 squared, nothing like that. You just have simple poles. And one information that will be important later on is that the canonical form is not unique. So I will remember you later about this. Okay, so why High functions are important after all? So special functions play a crucial role in mathematical physics. Everybody knows the Bessel functions, Legendre, Laguerre, Hermite, and so on. And they all these functions appear in physics problems like the I don't know the hydrogen atom, the quantum harmonic oscillator, the Laplace equation in electrostatics, and all these functions are part of the hypergeometric family. And here I quote a phrase of Humboldt's book on Hoyne's differential equation, and he said that it's not too much to say that about 1860, the special functions of mathematical physics were solutions of the hypergeometric equation in one form or another. And the Hoyne equation basically is a generalization of the hypergeometric equation, and hence possess a wider class of physical applications and a much more mathematical richness. So we can explore with the aid of the Hoyne functions more a wider class of physical mathematical physical problems, and is also a great avenue to explore pure mathematics as well. Okay, so now I will give you some definitions of that will play an important role in the next slides. So what we need to know about Hoyne functions basically is what are characteristic exponents, what is a confluence process, and what is the Hoyne equation symmetry group. So we may begin with the characteristic exponents. As I said, the Hoyne differential equation have four regular singularities. They are 0, 1, a, and infinity. And for each one of these singularities, we can calculate this thing called characteristic exponents. The exponents are basically a solution of a quadratic equation, the indicial equation. Here is a quadratic equation for rho here in equation 3 and 4. This equation 3 is valid for the singularities 0, 1, and a. In the singularity at infinity, you must solve this equation 4. So this we will have two solutions because it's a quadratic equation. So for each singularity, you have two exponents. And all this information can be summarized in an object that is called the Riemann P symbol. The Riemann P symbol collects the information of the location of the singularities and their respective exponents. So here in the first line of the Riemann P symbol, we have the location of the singularity. So one is located at 0, the other at 1, the other at a, and the other at infinity. And in the following two lines, we have their associated exponents. So the singularity at 0 have exponents 0 and 1 minus gamma. The singularity at 1 have 0 and 1 minus delta, and so on. And here I state a theorem that will be very important. So if we take two exponents, rho 1 and rho 2, of some singularity zj, and if the difference of these two exponents is not an integer, we can already conclude that there will exist two linear independent Froberman solutions at this singularity. And I will also remember about this theorem uh, afterwards. So now, what about confluence process? A confluence process is basically when you take two distinct singularities and merge them together. When you do that, you obtain a new differential equation, but now with less singularities and less polynomials parameters. Here, the confluence process that is going to be important to our case is the case when we take the singularity located at a and send it off to infinity. Now we will obtain this equation here, that's the confluent Hahn equation, that we only have three singularities, but the singularity at infinity is now irregular. So to finish this mathematical part of the presentation, I must tell you about the confluent Hahn the Hoyne differential equation symmetry group. So as I said in the beginning, the canonical form of a differential equation is not unique. You have several ways. Uh, you have several ways to express the same the a differential equation in the canonical form. So somehow we can modify the equation, but it stay in the realm of canonical forms. And there are two ways to modify the Hoyne equation, namely this transformation that is called the f-homotopic transformation, defined here in equation 7, is a transformation of the dependent variable, and a transformation that is called Mobius transformation, defined here in equation 8, that is a transformation of the independent variable. You can apply just a f-homotopic transformation or just a Mobius transformation, or maybe both at the same time. If you collect all the if you collect all the transformations that leave the Hoyne equation in the canonical form, you form a set that is actually a group, and this group is called the Hoyne's equation symmetry group. For instance, for the Hoyne differential equation, this group had 192 elements, and for the confluence case, the group is much smaller. It only has 16 elements, and these will also make a big part in our work. Okay, so enough of mathematics. Let's talk about physics. Here we begin with very simple stuff, just a Lagrangian of a MATLAB scalar field in a curved space-time. And we can, through the Euler Lagrange equations, we can obtain the corresponding field equation, that is the Klein-Gordon equation. And for globally hyperbolic spacetimes, you can define this Klein-Gordon inner product according to equation 11. This integral is evaluated over Cauchy surface, hence I required globally hyperbolicity. And yeah, here we consider the Schwarzschild spacetime that you are all familiar with, and we can also consider positive frequency modes according to equation 13. Here, these YLM are the spherical harmonics, and on the radial modes, this psi over here, I put this index n, which can take two values, the value right arrow and the value left arrow. The value right arrow are associated with radial modes that came from the horizon, whereas the left arrow is associated with mode that came from infinity. It's what Rafael in his presentation called the up modes and the in modes respectively, but it's just a different notation. So if you substitute these positive frequency modes into the Klein-Gordon equation, you can obtain a ordinary differential equation for the psi, for the radial modes. That is this equation 14. It's just a very simple equation, where this v is given by equation 15. The fields have this asymptotic behavior according to equations 16 and 17, where this r star is the tortoise coordinate. These a's are normalization constants, and r and t are related to the reflection and transmission coefficients. So now we wish to quantize the field, so we take our classical field and promote this field to an operator in a Fock space, and expand it in terms of positive and negative frequency modes, where here we have defined these new operators A and A dagger. They are the annihilation and creation operators, which satisfies this commutation relation given here in 19. And we use the Klein-Gordon inner product to orthonormalize the modes uh, according to equation 20. And using also the Klein-Gordon inner product together with the boundary conditions, we can calculate the normalization constant that is just 1 over 2 omega. Right. So We wish to consider a particle that is orbiting a charged black hole in a circular orbit. So for this, we define this current, the scalar current, uh, which localizes the particle at a radius capital R in the equatorial plane and with angular velocity capital omega. And we can calculate the emission amplitude of a particle with quantum numbers n, omega, L, n being emitted. This is a calculation at first order. And with the emission amplitude, we can calculate the corresponding emitted power according to equation 24. If we expand this emission amplitude, we can obtain this expression given here in 25. And we can see if we want to know what is the form of the emitted power, we have to solve the radio equation for this psi. And is the emitted power also must satisfy the selection rule here given in 26. Right. So in order to solve the radio equation, we consider this f-homotopy transformation in this new radio coordinate that is just the dimensionless coordinate. And if you make these transformations, we arrive at a confluent line equation in its canonical form, which is nice because we know the solution. It's just a confluent line function. So here we have the solution given here in equation 30, and these new parameters Q, alpha, delta, gamma, and epsilon, they are all defined here in equation 31 to 35. Okay, so here we have a plot of the radio modes, rather the absolute value of the radio modes for L equals to 1 for different values of the frequency in terms of the radio coordinate as well. The left panel is related to the modes that came from infinity, on the right modes that came from the horizon. So here we have the in modes and the up modes. And the dots represent the numerical solution of the radio equation, whereas the continuous pink line represents the analytical solution. And as you can see, the numerical and analytical solution are in very good agreement. And here we plot the emitted power as a function of the particle angular velocity. Again, we consider numerical solutions and analytical solutions. And once more, the left panel is related with modes that came from infinity, and on the right, modes that came from the horizon. And once more, the numerical analytical solutions are in very good agreement as well. So the interesting part is to analyze the low frequency regime, because something really weird happens here. If you take the general analytical solution for the radio modes and take the limit when the frequency goes to 0, uh, something weird happens because the two previously linear independent solutions degenerate into a single one confluent line function here in equation 36. And the first time that I saw this, I was really puzzled. But this explanation is pretty straightforward. This is due to the fact that the exponents at, at this particular singularity are 0 and minus 4 I m omega. And when we take the frequency to 0, the difference between the exponents goes to 0 as well. And 0 is an integer. So you are breaking the hypothesis of that theorem that I showed to you in the beginning. Hence, you lose linear independence as well. But you can find a second independent solution that is usually called logarithmic solution. And there are several ways to do that. And here we choose to find the solution by analyzing the confluent line equation symmetry group. And in order to do that, we first consider this identity that is true for A and B reals, and we can choose A and B to fit our problem. We choose A to be minus L and B to be L plus 1. So in this case, the left-hand side reduces to the confluent line function that we had here in equation 36, this one. And we can rewrite it in this manner. Now we employ the confluent line equation symmetry. Remember, it's a group with 16 elements, but we will only use two transformations. One of them is called T1 and the other is called T4. They are defined here in equation 39 and 40. And the strategy is to apply first we apply T1 and then we will apply T4. And we arrive at this new confluent line function here in equation 41. And the good news is that this new confluent line function is now linear independent to the first one. And hence, we can express the general analytical solution for the low frequency regime as a linear combination of these two Hoyle functions, according to equation 42. Very nice. And you can also look for the relation between confluent Hoyle functions and hypergeometric functions. And they are given here by equations 43 and 44. And what is interesting is that these equations 43 and 44, these are basically hypergeometric representations of the Legendre functions. So these would be the PL and this would be the QL. And this is a very well-known result in the literature. When you take the scalar field in shorter space-time, you take the radial sector and analyze the low frequency regime, you get Legendre equation. So we basically are arriving at the same result, but with a different route. Okay, so now I will just make a summary of everything I said to you. So we have obtained analytically the radiation emitted in terms of the confluent High functions. We present some consistency checks comparing the numerical and analytical solutions, obtaining great agreement between them. And in the low frequency regime, you have shown that the Hoyle functions become degenerate. But using the confluent Hoyle equation symmetry group, we are able to obtain a linear independent pair of solutions. And yeah, I think that's all. And thank you.